So the results look like this. Here the throughput, here the load, here the coding gain. If you, as a student, for your student thesis or for your diploma thesis, master thesis, are going into that and say, hey, I know that my load looked like this, and now the measurements look like this. Would you be satisfied? Or would you say, totally different? That's an easy question, right? So, do you recognize some similarities? Good. So at least you see they both go up for a while together, then they diverge. The one goes down and the other one stays up there, right? Okay, looks, and this is real stuff, right? So something that you calculate on paper and something that you see here, interesting. If you look then at the coding gain, you don't get the 100% as we wanted to have it, so doubling the capacity, but we got 60% out of it. Good. And then the first impression is, okay, you say everything is fine, right? So it goes up, it goes down. The other thing is the blue line goes up and then it goes down also a little bit. That was not expected, right? Nevertheless, in the beginning we were quite satisfied, right? Here you see the analytical results, here the measurement results, and you said, okay, let's do it again, right? Maybe there is some measurement problem. We set it up again. We said maybe we measure at night. It doesn't matter when you measure. At night, without interference with the students there, it was always the same. We had this dip. And I would say this cost us 2 PhD students entirely to explain us what happened here. Nevertheless, as a discussion, we say, okay, coding gain is with 1.6 a little bit lower than expected, and the throughput of NC is not stable after reaching its maximum. So why? Then we said, okay, let's look at the plots just for Alice and Bob. And then you see, okay, this is Alice and this is Bob. And with and without network coding, it's more or less the same. Even in the coding, it's not that one is worse than the other, okay? But you see some fluctuations here. So here, the fluctuations are the variance is low, and then the variance goes up. So it seems that sometimes the load is very low, and sometimes it's high as expected. The same here. And what was the main assumption for our model?
Both have the same data to transfer.
Correct. And it seems like they are not doing this. I mean, the laptops are doing that. But with the medium access control, it can happen. I don't know how much you know about IEEE 802.11, but it can happen that you try to access a channel, you have to back off, the other one sent more packets already, and the delay in the middle, as we had it before with the blue packets, how long do we have to wait, right? So what is the impact of non-symmetrical traffic? So there is something what we did in the paper that you saw in the beginning. We said, okay, coding gain versus links share. And it's quite easy. The gain that you get is 1 over 1 minus x, which is the load, the share. Let's show you the share of the load. So if you have a 50-50 share, then you can expect 100% gain. But if you move a little bit to the left and a little bit to the right, it goes down. And suddenly, this is what we measured. The green value, the green bar here tells you 20% we can explain by unsymmetrical traffic that comes in. Not over the source level, it was okay, but the medium access in the end made the change. But we did not have 20% loss. There was something more than that, right? And in order to understand this, we looked into the relay and said, tell us, when there's a certain load, what are you doing with the packets? And this is the overall amount of packets the relay had in the beginning. And what did it do? Some of them were coded and some of them were forwarded. I told you that we don't wait forever. If you have a very low load, packets come from the left and packets come from the right. But we don't wait forever. So if there's a backlog, we just spit it out. But this is already paid off with our first 20%, right? So if you have enough load, you see that the coded packets go up and the forwarded packet go down. That's fine, right? But if you go higher and higher and higher, suddenly at 3000 kilobit per second, the forwarded packets come up again, and the coded packets go down, and the overall packets go up again. And this is where we pay the other 20%, right? It's a buffer bloat problem that we found out later with the queuing system. It's not so easy. But we'll come back to that. So one is really not symmetrical traffic. The other one is the architecture of the platform. So what you see here is if we measure now the power, that was easy because you just need a tool for that. You have the throughput, you measure that, and what you have now is the energy per bit, and this looks more or less exactly what we expected also with our analytical one. So if you compare these two together, it's exactly the same behavior. We were quite happy with that. Throughput again and energy per bit, fine.